Right, so this is what we were talking about last week. Right, so we mentioned some very basic things last week about tension and compression and elongation, shortening, right? So whenever a material that elongates along a certain direction, that is due to tension. And similarly, for a certain piece of material that shortens along a certain direction, that is due to compression. Okay, those are the very basic things that we covered last week, and then we talked about bending. So we said elongation corresponds to tension, shortening corresponds to compressive force, and then what about bending? What causes bending? So the focus last week is bending is due to something called bending moment. So it's actually due to a moment, not a force. That is something you need to bear in mind. Bending is not due to force, it's due to a moment. And that moment, we call it bending moment. That is the concept we covered last week. And there are also a few technical terms we're going to use from time to time, particularly in the quiz and in the examination. Don't mix up those two terms, sacking and hawking. We also explained how to sketch those deflected shapes last week, right? And I also show you an animation that describes how a beam bends like that, sacking, and what happened to the material. And then we come up with this sort of a summary figure, right? So this figure basically summarizes everything that I want to say about bending, right? So in case of sacking, you have part of the beam in compression and part in tension. Although the compressive force and the tension force are not uniformly distributed, they vary. Right, the maximum is at the top or the bottom, depends on sacking or hawking. Right, and from this diagram we have derived a very simple formula what bending moment is. And of course, you don't need to do any calculation for this formula. I just sort of explain what bending moment is about. And then we cover a few examples. The most important thing in these examples is you need to know how to sketch the deflected shape based on the given location of the supports and the loading. Right, you try to sketch the deflected or deformed shape, and from the shape you can tell whether it's sacking or hawking. And from sacking or hawking, you can tell which part is in compression and tension. And then you know which reinforcement is the main reinforcement, the top or the bottom. Right? So in this case, the bottom is the main bars for bending, and then the top it's secondary sort of, and it's not for bending purpose. Right? That's what we explained last week. And then we said a few things about this beam, the cracks, and also the direction of the tension. They are perpendicular to each other, right? The direction of the cracks are perpendicular to the direction of the tension. Right? And in this case, because this is sacking, so the cracks are at the bottom of the beam. We'll also come to shear in a minute. So this is for cracks due to bending, so that's cracks due to bending. Right, sometimes there's another word for bending is flexure, Flexure, that's meaning the same thing. right? Flexure is the classical English word for bending. And then the figure below, that's cracks due to shearing. So we'll come back to this figure in a minute. Right, and then the other diagram, or the second example, is this two-span two-span continuous beam with loading all over the entire beam. So we try to sketch the deflector shape again. And from this, we divide the beam into a few parts, and part of them are in sacking and another part in hawking. And from that, we can tell which part is C or T, right? And actually, in last week, in class exercise, there were also 1 or 2 questions about those deflected shapes. Right, so you should be able to sketch those things. And that kind of thing, of course, will also appear in the quiz or exam. So make sure you know how to sketch those deflector shapes. That's the third example we covered last week for cantilever, which is a very common type of structural element in building structure. The figure below illustrates what that is. Right, that is a cantilever supporting a balcony above. So all the loading will be supported by that beam and fixed supported only at one end. Right, so that end actually corresponds to that thing in this figure. So in this case, the beam is under hawking and then tension at the top. So that's why the main bar is at the top. And in the bottom bar is not it's secondary reinforcement. Right, and then always there are some shear links, so-called shear links. That is what we're going to cover today. Right, so those are the things that we covered last week. And then we continue with, we'll come back to this diagram in a minute when we finish the discussion about shear. And let's look at this one. This one we came across this back in week 8, the first lecture on structure. Okay, right, and you can see in all these steel beams we try to make openings in it in order to reduce the weight. And you can see the openings, what we said is the openings, if I just sort of draw one of these. No, if I draw one of these here. Right, so what you can see here is elevation view, right? So that is your top of your beam, that's the bottom. And then there's a center line. Right, that center line, we don't call it center line. Last week we said that center line is called neutral axis. Right, that beam is under bending, so we can draw a diagram just like what we did last week, showing where's the maximum compression or tension. So we can draw a diagram like that, where let's say this beam is under hawking, so the top part is in tension. Right, and then the bottom bar is in compression. Right, so like that. So you can see at the neutral axis, or close to the neutral axis, the compressive or tension force is relatively small compared to the top or bottom. That's why we should now be able to explain why we make an opening around the neutral axis. Whenever you try to make an opening, don't try to open at the top or bottom. Try to make it near the neutral axis. Right, because this is the area where the stress is, or the force is relatively small in this region. Right. So this part of your beam is subject to relatively small compression or tension. And that's why you make your opening around that region, not near the top, not near the bottom. Right, so and after that we can come to shear. So the next two slides are actually about shear. Right, so first of all, so what is shear force? Chinese name for Chinese translation of shear force is 引力. So to demonstrate shear force is easy. It's not something difficult to demonstrate. Right, so first of all, let me just demonstrate what is 引力. Right, so everybody knows what that is. It's a pair of scissors. You know how it operates. That is trying to, if you want to cut something, right, you cut it like this. Right, so everybody knows how to use a pair of scissors, but I doubt nobody have ever thought about why a pair of scissors can cut things like that. What's the principle behind? First of all, if you notice this pair of scissors, there are two metal plates, 兩塊刀片. And when you try to operate, these two things, they come together in opposite direction at the same time, right? When you try to cut things, these two things go in opposite direction at the same time. And they are not cutting on the same line. They are actually separated by a very little distance, but they are never on the same line. Right? If they are on the same line, then you can't cut anything. They are separate by a certain very little distance. So that's why you can cut things like that. Okay? This exactly represents a pair of shear forces. So shear force, by definition, it can be defined like this. So you got a little piece of material, whatever that is, a piece of paper, a piece of plastic, a piece of steel, whatever, and you try to cut it. So what you need to do is you apply a pair of forces, right? Just like a pair of scissors. You apply a pair of forces and they act in opposite direction at the same time. Opposite direction. So one going up, the other one going down, like this. And the distance between these two forces, it doesn't matter as long as it is not zero. So if that distance, if the length of that thing is a, so a definitely is not zero. And then those two forces act in opposite direction. Or you can have the force on the left going down, the force on the right going up, like that. Same thing. As long as you got two forces, a pair of forces acting in exactly the opposite direction and separated by a certain distance. That distance, of course, is not zero. Right? And if you have a pair of strong enough scissors, 你可以幻想如果你較錢夠厲害嘅話 you should be able to cut the piece of concrete, not just paper, right? So here, of course, I'm just cutting a piece of paper. But if you have a strong enough pair of scissors, you can cut a metal sheet, you can cut a timber, even a piece of concrete, you can cut it, provided that your pair of scissors is strong enough, right? So what that means is, if that pair of forces is large enough, then you should be able to cut anything. Right, so that is basically the definition of shear force. The second thing is why we need to know shear force in a beam. Remember, what we're talking about is a beam. So to explain that, I need to sketch a little thing. So let's say, assume that I have a beam like this. It doesn't matter how long the beam is, whatever. It's not zero anyway, so the length is not zero. And it's under some kind of loading, whatever. It bends, right? The beam bends, so there is bending. So I also assume that it's under sacking. So let's say the beam is under sacking. So when the beam sag or bends like this, this is what we call sacking. That is due to bending moment, right? So where are the bending moments? So if a beam bends like this, I think I've demonstrated last week. How do you bend a beam like that? You need two moments. One on the right. My right hand needs to turn in the anti-clockwise direction. And my left hand needs to turn in the anti-clockwise. Sorry, this is clockwise. This is anti-clockwise. And then you do it at the same time. And then the beam will sag. Okay? So, where are the bending moments? So, this is one of the bending moments. That is another bending moment. That will sag or bend your beam into sagging. So let me call this moment M, and this M prime. And the length is A. Obviously, A is not zero. And how long is A? Doesn't matter. A can be anything, just not zero. Right, so now I know that this beam is bent into sagging by these two moments. And let me just assume, in general, just assume in general that m and m prime are not the same. The magnitude are not the same. So if these two values are not the same, then what happens? M is clockwise, so this is clockwise. M prime is anti-clockwise. Right? So if I say they're not the same, and if I assume that m is smaller than m prime, what does that mean? That means this clockwise moment is smaller than this anti-clockwise moment. 順時針係細過逆時針. So what happens? You have an object and you have a clockwise moment here, anti-clockwise moment there. And the anti-clockwise is bigger than the clockwise. They are not the same. So this thing is supposed to rotate. Right? So that implies if I have a beam with these two moments, my beam will rotate in the anti-clockwise direction. But this is not true. Actually, my beam doesn't rotate. If I assume a situation like this, my beam will rotate in the anti-clockwise direction. 呢條 beam 應該會逆時針喺度轉。But actually it doesn't rotate. 但係佢實質上係冇轉到。So what that means is something is missing from this figure. 有啲嘢漏咗。Something that should be able to balance this anti-clockwise rotation. So what could that be? That is my shear force. In other words, there must be a pair of shear force like this. Left up, right down. That try to rotate this beam in the clockwise direction. 順時針. So this clockwise will balance the anti-clockwise tendency. They try to cancel out. Okay? So this m prime minus m is not 0. The anti-clockwise is larger than the clockwise, so it's not 0. That thing should be balanced by something. That anti-clockwise moment should be balanced by this pair of shear force. F times the distance between them. So on the left side, you have anti-clockwise. On the right side, you have clockwise. So from this equilibrium, we know that whenever you have bending moment, you have shear force. Or in other words, bending moment and shear force, they coexist with each other. Just like two sides of a coin, 好似一個銀嘅公同字，佢哋永遠都一齊，有公就有字嘅。So whenever a beam bends, in general, you have bending moment. And the bending moment in general are not the same. So there must be shear force. Right, so from this simple discussion, we understand that there must be shear force in the beam. Right? shear force. Right, so we now understand when a beam bends, that is due to bending moment, and whenever there is bending moment, there will be shear force. So the next thing is, what happened to your beam when there is shear force? Right, so last week we know that when a beam bends, there will be compression and tension, right, like this. When a beam bends, there will be compression and tension. What about when a beam is under a pair of shear force? What happened to the material? So here, we're going to explain what happened to the material when you have a pair of shear force like this acting on your beam. So let's say I have a piece of concrete, assuming this is a piece of concrete, right? A square piece of concrete. So this is my concrete. And let's say this is under a pair of shear force like that. Right, so this is concrete. So the next step is, if you have a square piece of concrete under a pair of shear force, what happened to the shape when you apply a pair of shear force like this? So that is not something very difficult to imagine. I don't have an animation, but it's easy enough. Right, so assume this is just a square piece of concrete. And what you're going to do is apply a pair of shear force like this. The left hand going up, the right hand pulling down. So what you should notice is the change in the shape. This is square. So when my left hand push up, right hand pull down, what happened to the shape? 呢個係咩形狀? It changed to this parallelogram, 平行四邊形. Okay, just like that. Right, so that is already on your handout. That shape changed to something like that. That's a parallelogram. This is how it deforms under a pair of shear force. Right, so what I'm going to do here is I will try to combine these two sketches together into one, and I put it here. I try to combine these two. So my concrete originally it's a square. When I apply a pair of shear force, it changes, the shape changes, it deforms into a parallelogram. So I use dotted line to represent. Right, so this is my parallelogram. That's my original square. These two shapes, I try to combine them into one like that. So what I want to do is, I want to look at the diagonal, 對角線. If you look at the diagonal here, that's the original diagonal of the